Hi there, my name is Heath. This is section 11.1, Introduction to Sequences and Series. Up until now, we've studied functions whose input values represented real numbers. The fact that an input variable x can take not only the value 3, for example, but values arbitrarily close to 3 is what makes the concepts of limit, continuity, and differentiation possible. What happens if we remove that underpinning? A discrete function, also called a sequence, is a function whose domain is restricted to values in a discrete set, usually the set of positive integers. We can use discrete functions to represent the output of iterative processes rather than processes which occur gradually. Here's an example. You're designing a computer program which can play chess against a human opponent. Each time when it is the computer's turn to play, the computer examines the board for possible moves and uses a weight-based algorithm to select a strategically strong move. On each turn during a recent match, the number of moves analyzed by the computer is shown below. On turn 1, the computer analyzed 20 moves. On turn 2, the computer analyzed 26 moves, and so on and so forth. This is an example of a sequence. The input value is the turn number. The output value is the number of moves considered by the computer. The turn number has to be a whole number. There's no such thing as the 2.001th turn. And so we can't do things like limits as x approaches 3 or the derivative is at x equals 4 or something like that, because we can't approach these points arbitrarily closely. The points have to be separated by a distance of 1. So the input value variable is discrete and not continuous. We use notation like f of x comma y to represent a continuous function. And we use notation like a sub n to represent a sequence. The a tells us which sequence we're talking about, and the n tells us what the input value is for the sequence. N is the input variable, and it's listed as a subscript. Let's list the first 6 terms of the sequence. The first term would be a1, or a sub 1, and that would be 1 is my input value, so I plug in 1 for n, 1 plus 1 over 3 times 1, which is 2/3. A sub 2 would be 2 plus 1 over 3 times 2, which is 3 over 6, which reduces to 1/2. I'll do one more. A sub 3 is 3 plus 1 over 3 times 3, which is 4 over 9. And if we kept going, a sub 4 is 5 over 12, a sub 5 is 2/5, and a sub 6 is 7 over 18. We can write this more compactly as a list enclosed in curly braces of the terms of the sequence, and the sequence continues on infinitely far. We say the sequence converges to a value L if, as n gets larger, the values of a sub n approach the value L. Another way of saying this is if we allow ourselves a small error tolerance, epsilon, there will be some point in the sequence after which all of the terms will be between L minus epsilon and L plus epsilon. We can state this as a theorem. Let a sub n be a sequence. Let L be a real number. We say that the sequence of a sub n converges to L if given any error tolerance epsilon greater than 0. We can find some stage of the iteration so that for all future stages of the iteration, the value of a sub m lies in the interval L minus epsilon, L plus epsilon. So let's prove that this sequence converges. We start by looking at the terms of the sequence. The first term is 1 over 2 times 1 plus 4, which is 1 over 6. The second term is 1 over 2 times 2 plus 4, which is 1 over 8. And since the denominator is getting larger, it's pretty easy to tell from looking that these terms are approaching 0. It's easy to tell, but that's not a proof. How would we prove this fact? So if we chose an error tolerance of, for example, epsilon equals 0.01, we would need to show that after some point, all of the terms of the sequence were in the interval from negative 0.1 to positive 0.01. But we can solve that inequality. These terms are always positive, so I don't have to worry about the negative 0.01 side of the inequality. I just have to worry about being less than positive 0.01. So I substitute the formula for a sub n, take the reciprocal on both sides, that changes the direction of the sign, subtract 4, and then divide by 2, and I get n is greater than 48. This is a key step in proving convergence. I've shown that once I reach the 48th iteration of the sequence, all of the terms after that point, A49, A50, A51, they won't be exactly 0, but they will be close to 0 within that error tolerance we selected. The error tolerance we selected, again, was 0.01. However, the definition says that we have to show this, that we can solve this inequality for any tolerance and not just the one that we chose. So we have to go back and redo those steps, but leave the tolerance as a generalized epsilon and not as a specific number. So not placing a number here, leaving this as an epsilon, I get 1 over 2n plus 4 is less than epsilon. Take the reciprocal on both sides. This is what we did last time. And then subtract 4 from both sides and divide by 2, and I get this expression right here. And now I can conclude that no matter what the error tolerance is, once we have reached a stage that is greater than this amount, all future stages will have an output value that's within the error tolerance we started with. And that's a proof. So let's try another example. Let's show that this sequence converges. The first thing we want to do is just examine the sequence. When n equals 1, I have 2 over 1. When n equals 2, I have 3 over 2. When n equals 3, I have 4 over 3, 5 over 4, and so on and so forth. Each of these numbers is getting closer and closer to 1. So an examination tells me that the sequence is converging to 1. All of these terms are slightly greater than 1. But they get closer to 1 as n gets large. So then the second step, and after you've done this for a few times, you can skip the second step. But for right now, let's try this. Pick a tolerance. So I'll use epsilon for this example. I'm going to use epsilon equals to 0.1. And that means that I need for all of my values to be between 1 minus 0.1 is 0.9, and 1 plus 0.1 is 1.1. And since all of the terms are greater than 1, this is the controlling side of the inequality. And so we set a sub n less than 1.1. N plus 1 over n is less than 1.1. Multiply through by n plus 1 is less than 1.1 n. Subtract n from both sides, and then multiply by 10. 10 is greater than n, or n is greater than 10. Once I have reached the 10th iteration of the sequence, every term past that sequence will be within the tolerance that I want. It will be that close to 1. And once we've seen how the calculations work out for a specific number, redo these calculations using epsilon as a variable. So this was 1 plus epsilon. So I will need for a sub n to be less than 1 plus epsilon. So n plus 1 over n is less than 1 plus epsilon. N plus 1 is less than 1 plus epsilon times n, which is equal to n plus epsilon n. Subtract n from both sides, and we would get 1 is less than epsilon n. And then divide both sides by epsilon, and we get n is greater than 1 over epsilon. And so when n is greater than 1 over epsilon, a sub n is in the interval 1 minus epsilon to 1 plus epsilon. And that completes the proof that this sequence converges to 1. A sequence diverges if it does not converge. There are two ways that a sequence can diverge. It can diverge because the terms approach positive infinity or negative infinity. The sequence of perfect squares, 1 squared, 2 squared, 3 squared, 4 squared, 5 squared, and so forth, diverges because the values just keep getting larger and larger and larger, and they don't approach a value. The other way that a sequence can diverge is to diverge by oscillation. That the pattern of the numbers goes up and down and up and down and up and down and never approaches a single limit. The pattern 1, 2, 3, 2, 1, 2, 3, 2, 1, 2, 3, 2, 1, 2, 3, 2, 1, 2, 3, 2 never settles down and approaches a specific number. It just keeps oscillating between 1 and 3. If we want to test a function for convergence, sometimes the continuous function theorem helps. This is the continuous function theorem. Let a sub n be a sequence, and f of x be a function which is continuous from 0 to infinity, and which equals a sub n for the natural numbers when x is equal to n. Then if the limit as x approaches infinity, if the continuous function converges to a value L, so does the limit as n approaches infinity of the sequence a sub n. However, if the function diverges, we can not automatically conclude that the sequence diverges. It's possible that the continuous function can diverge and the sequence still converges. We will see an example of that, but it won't be the next example. It'll be one later on. Let's show that this sequence converges to 0. If I change this from a sequence to a continuous function, natural log of x over x plus 2, and try to take its limit, well, it's in an indeterminate limit. Natural log of x goes to infinity, x plus 2 also goes to infinity. But we can use L'Hopital's rule to evaluate this limit. The limit of f of x is the limit of natural log of x over x plus 2. Take the derivative of the numerator, I get 1 over x. Take the derivative of x plus 2, I get 1. This limit approaches 0 over 1, which is equal to 0. This function right here is discontinuous at x equals negative 2, but the continuous function theorem says that it has to be continuous only from 0 to infinity, and it is continuous from 0 to infinity. And therefore, this discrete function converges also. Let's look at this sequence. Show that this sequence converges to 0. We can't use the continuous function theorem because this function oscillates between 1 and negative 1. And so this function diverges because it doesn't converge to a specific number. But if I'm not looking at the function, the continuous function sine of x pi, I am looking at the discrete sequence sine of n pi. N can only be a natural number. And so these terms are sine of 1 pi, sine of 2 pi, sine of 3 pi, sine of 4 pi, sine of 5 pi, and each of these is equal to 0. This sequence is just a sequence of constant values that all equal 0, and a sequence of constant values converges to 0.